Hi, sir. Hi, doctor. You are muted.
Oh, okay. It was muted. Sorry about this.
Okay.
So now can you all hear me?
Yep, can hear you, doctor.
All right. Um, yeah, I mind. Sorry about this. So I was saying my plan is to share these solution steps for, okay, we're going to cover only the section one, which is the constraint approximation with Lagrange multipliers, and also section 2, but because of we only have now less than an hour, I cannot go through, in fact, many of the problems here. My plan is only to share the solution for 3B here, and also for this optimization in section 2, question number 2. So before I proceed, do you actually have any other problems here that you want to see? We can discuss your question first before I discuss my solution for these uh, two questions. So out of this, like for section 1, you have 5 problems. Any problem you want to see other than 3B? And for section 2, there are 3 problems. Okay. Now, let's see. Yeah, we'll start with 3B first because and this question 2A here, it will take more time. I don't think I can finish if I want to do every step, even for this only 2 problems. So we'll see. So we start with 3B first. Okay. What I want to do now is share my OneNote. See. Page. So it's gonna be tutorial section 2, question 2, question 3B. Okay. Okay, you should be able to see my OneNote now. Extend the page. So what is this? Okay, can do this. We are going to maximize this part. Easier if I just copy, crop and paste in here. All right. So this is the statement of the problem here. If you the reason why I choose this problem is because this is like an extension of what we discussed some time back with the case where there are, in a single problem, maximum and minimum values that we can determine from calculating these Lagrange multipliers. And at the same time, the statement here somewhat maybe different from the usual statement. It says here, to this constraint G of X and Y equal to C. That's all. Yeah. And then in the subsequent statement here, so subject to this whole equation for the constraint. So immediately you can, or you should already think that, okay, this is your G. And because in here, we start with G xy equals to C. Remember,
Doctor, are you using your OneNote?
yeah.
I can't see it on your screen.
Oh, okay.
Yes, yes,
Sorry
doctor.
about this.
So far, I'm still seeing the PDF page.
Thank you for, oh heck. Instead of sharing, wait. On presentation. Okay, I have to cancel this and oops. Okay, give me a minute here. Those whiteboard. Okay, there's a problem here. I have to stop sharing first, and later on, remind me if we don't see the PDF. Okay, maybe I can choose both for notes and there. Share. You see now my OneNote, yeah?
Yep. Yes, doctor.
All right. Sorry about it. Thanks. Okay, I also share this preview. All right. So, yeah, as I mentioned here, in the PDF, it says subject to Gxy equals to C, where C is this variable that constrains it. But at the end, we want to deal with this specific statement. This is basically 4x squared plus y squared is that G, yeah? But it's written in a way that if you want to
600.
include this 8 as the constraint value, so we usually write it in this way, right? So basically we write it as G equals to 4x squared plus y squared minus 8. And then when we set G equals to 0, we get back to this statement of the expression of the constraint. So it, to some of you, can be confusing, but this is just another way of saying the same thing here that we said before. So the idea of the C has constant values, which doesn't matter when you want to take the Lagrange multipliers, because C is just constant, it will not appear in the gradient equation. So you just work as usual, yeah. you take gradient of f, set it equals to the Lagrange multiplier lambda and gradient of g. So what you have now is what is f? This can get, so this is where you have to be careful with how you take the partial derivative, yeah, because this x and y can be mixed up easily. So from what I just do this in my head, that's the first partial derivative is with respect to x, so that means this is 4y. So, and then the other one is because it's being with respect to y, so it'll be 4x. And then you have this Lagrange multiplier, and then again this, so you're going to take the gradient of this whole expression here, which we can ignore the constant, so you just have this. So with respect to partial g partial x, you get 8x, you agree? The rest are constant. And then the other one is partial g partial y, which we only give us 2y. Up to here, you all can, you know how to do this, right? There's no problem. Okay, you all clear? Now, this is where we can set up this as simultaneous equations to the goal is to have the values for x and y. We don't really care what lambda is. Lambda is just a value that ties these two gradients together. So the first equation is, I will already simplify this. So I just gonna can write y equals to, what's it, 2x, right? 2 lambda x, agree? And then the second equation is x can be equal to what? Okay, so for this, it'll be the other way around. So because I'm canceling 2 here, so 2x equals to lambda y. Yeah. So remember, this is still undetermined because we have 3 unknowns and 2 equations. The third equation is the coming from the constraint where you have this 4x squared plus y squared equals to 8. Okay. 4x squared plus y squared equals to 8. So with this now, you can already find xy, but this is where we have to, because it will have, as I mentioned, multiple values. As you can see, the question asks for minimum and maximum, right? So you expect it to have multiple values for x and y. So this is where we proceed. So I'm gonna just divide this equation 1 and 2. So that means I cancel lambda. So what I have is y equals to 2x is going to be 2 times x over y. So this is, you see, right? Because there's a quadratic relationship now. 2y square is 4x square. This is where you don't want to simply cancel, right? Because we want to have, by quadratic we have two roots and we want to keep that two roots intact so we can solve for it. So so I'm going to, because now we have y squared equals to 4x squared. This is question of communication in mathematics here. I'm going to, okay, we can just call this equation 4. Eh? So basically, I want to put 4 into 3. Yeah, so that I have 4x squared plus 4x squared equals to 8. So that's basically make us x squared equals to 1, right? So this is where, let me check. I don't make any mistake. Give me a second. Yeah, okay. So now you can imagine, because of this square values here, that means x is either plus 1 or negative 1. So you have two sets of x. And this is another thing. So let's just put this as it's in a set. Yeah? Now, if I have this for, so at x equals to this, these are coordinates. Right? At x equals to plus 1, you can use any, so from equation 4, for example, you can see that y is, okay, this is where, okay, let me just, I think I have to write it so it's easier to see, right? Y square is 4. So now with this, you have y having two solutions, right? Plus 2 and minus 2. Okay, so this is where you have to, because now you have two values of x and two values of y. So you have 4 points that you have to evaluate the values of f so you can tell whether, because you have to pick out of these 4. Let me just write first. You have, let's take the positive 1 and 2, and then you have 1 and 2, and then 1 and negative 2. Is it? Oh, wait. Am I doing some careless mistake here, or if this is correct? I think it's correct, yeah? So x squared is 1. So 4 is y squared is 4, right? Does anyone have different values? Just let me know. I think I'm doing this. My simple calculation is correct. So you have 1, -2, and then you have -1 and 2, and then also -1 and -2. So from here, this is where you evaluate the value of f. Yeah, because since f is for xy there, so let's just write it in here. Yeah, f is 4 times x times y. So f12 you get 8, correct? F1 -2 you get -8, and then f -1 2 you have -8, and then f -1 -2 you have -8. Sorry, that's +8. Okay, so you see that this gives us two locations of this. This is max, this is also max, and this is min, and this is min. Okay, this is now our answer. Yeah, so this is not a, as I see it, not a usual case, where you have multiple maximum and multiple minimum in a problem, but it can happen, right? That because as you can, now that you see these values, you can sort of picture that these two functions f and g, they have some symmetry in this 3 dimension. So if you, now to show you this, I found a really cool online calculator. I don't know if you've seen this website. Let me, I will show you later. I have to find it again. It's a 3D, okay, GeoGebra. So nice name too, GeoGebra.org. Okay, I will just paste this link on Telegram so that later you can test it. It is quite fun. Yeah, Fikri was asking, let me come back to it, but just want to set this calculator thing here so that you can see. Share content, Google Chrome. You can see my Google Chrome, yeah? So this is a nice way to visualize a simple function. Like, let's say I have 4 times x times y. Um, Why doesn't the... Why can't this appear? I was testing it just now. There is... Was playing around with this. It seems to be working really fine just now. Okay, so this is for sine of x, but if I do, if I want to do this, why? Okay. I think there's something wrong with probably my desktop here. For my laptop, I can visualize this on my desktop, but for some reason not with my laptop, which is quite strange. What I want to do now is let me... Okay. Where are we still left? I don't think I can finish completely for the golden section calculation, but let me do this first. Okay. Try to crop this picture and show this to you. Dropbox. Oh, there's a GeoGebra 3D. Okay, thanks. Okay, that is the reason. I didn't know there's a GeoGebra 3D in. Yes, okay. Thanks. Then log x times y. So that's the reason. So okay, this is the nice picture there. So this is the F. So you can see it's like it has some kind of, we don't really call it symmetry, do we? It has a symmetry, let's say, with respect to this plane. Like there's like there's a plane of x and y, and you have a symmetry there. And so the other one is basically a let me just try to write it. It's not circle, but more like an ellipse. Yeah. Huh? No, this is this is a cone. It's not that I want. I need a different way of inputting this. Just test. It's quite user friendly since I just tested it today or just now basically, and it, yeah, you can learn it very quickly. So you see here, So we want to find a location on this f, which has like this curve. You see there's like a quadratic function there, and it's being constrained by this location, location of, what did you find here? 1 and 2, I believe. Is it 1 and 2? So you can see that because we have, okay, if I do like this, X has these 4 points there, and then Z has for the like 4 values, the negative part, and then the positive part, and the negative part. So this is where you so switching back to my OneNote, it's where you get these two values of maximum and 2 values for minimum. Okay, now Fikri was asking about how do I get the gradient. Did I messed up? So let me I okay. X plus 4y gradient of f. Okay. So let's do it here. Let me try it as, okay, now it's blue. Okay, never mind. So f is 4xy. Happens again. Okay, I'm quitting OneNote. I will open it now and share. OneNote. Share again, OneNote. Okay, so when you look at f, so what is again gradient? Now it's black again, sorry about this. So gradient is partial f over partial x and partial f over partial y. The first thing I want everybody to be clear by now is that when you have a scalar function like f here, taking the gradient, you should by now automatically picture that when you take the gradient, it's a vector. Yeah, so if it's a vector, then it has an x component and y component. So the x component of this vector is given by the partial derivative with respect to x, and then the other one is the derivative with respect to y. So if I were to take this whole expression for xy with respect to x, then this is basically a linear function with the coefficient of 4y, right? You're following? So we get that taking the derivative respect to x give us this coefficient of this. It just happens to be y as a variable too. That's just the concept for us, and because of this partial derivative. Same thing here. This is partial derivative respect to y. So y is the active variable here. The rest are like coefficients. So this is 4x. Okay. Is everyone clear? This is just from your revision of vector calculus. Okay. Right. So that should be, I hope, clear with everyone. If it's not, just ask me about this. The final evaluations here. Eh? Okay. We don't have. We have like basically 7 minutes left. I'm just going to talk about the next problem. Yeah. So where is my practice problem question here? So this problem. Okay. Think I can just zoom it a bit. Put this. Oops. I can put it on OneNote and then just explain to you how I would do this. Yeah. Section 3, I believe. All right. Of course, if this is to be done in a test, for example, I already will give you, or I will sometimes expect you to recognize, given this function, where the maximum point or minimum point is, and then you decide the limits, yeah, the first limits to put that bracket, the first brackets in. Yeah, but since you're doing this with as a practice problem, you can, okay, let's use that GeoGebra here. So if I were to, I don't know if I can see, delete this. Can I, oh, what's that? So 4 times x, can I basically, yeah, just go to the 2D calculator. Just leave this. Okay, 4 times x plus, what's the value? What's the function is now? Minus 1.8 times x square plus 1.2 times, oops, 0.2 times x to the third power, then minus 0.3 times x to the fourth power. So now you see there is a single maximum. That's what we want to put the bracket in. And I already give you the limit, which is from -2, which is way down here. Wow, -2. Yeah, because of this fourth power, right? And then from -2 to plus. Okay. I think there's an error in my looks like an error. This upper should be +4, eh? Otherwise, I don't think you can be not. What's my not? Oh, 2 to 0. Okay. Yeah, the limit doesn't. Did I change this? Yeah, okay. It should be from -2 to +4. Yeah? So this is something that is not right in my. I will correct this later. Should be +4 here. So for the time, huh? If you set this limit and since we're doing this as a practice problem, as I mentioned, it's much faster if you do it on using MATLAB. Yeah, you can just reuse the variables and then keep calculating here. What I want to do now is okay, since we have to stop now. Okay. Let's see in this online calculator. I don't know if they have a tool to find the maximum point here, but as you can see, okay, first of all, did I get this plot right? 4x minus 1.8x squared plus 1.2x cubed minus 0.3x to the fourth. Maximum. Where's my function here? 1 point negative. Okay. On B. Okay, I was going to tell you that because this asks for this epsilon s here is the relative accuracy. Relative means you should take the relative error So the difference between the exact value of the function where you can use in MATLAB this fmin PD, I believe. So yeah, I forgot already. F min BND. Yeah, okay. So you can find the maximum. You can use fmin BD to find the maximum value also, not only minimum values. Then you can take the difference of the value that you get from this cone section method and find the relative error. That's what I meant here. But anyway, since we're out of time, okay, I'm going to stop sharing. If I have some time, I will just give the values that I calculate, so you can compare with your own calculation. Okay. So we have to stop now. Any question before we finish? So Alvin is good. 50 of you are here. Thank you for coming. So I will see you. Okay, since you are here, I think I will also announce this later. So tomorrow, we will go back to the golden section method, just a short one for the algorithm, and then I will move to linear programming. And I will also put up an assignment for this golden section, the MATLAB assignment. And also, we will have lecture as usual this Friday. Yeah? But I know that maybe I know maybe you are already in Raya mood or whatever. Okay, fine if you don't want to attend, but yeah, as I always say, I will have the recording on e-learning afterwards. All right, so see you tomorrow. Assalamualaikum and bye-bye.
Thank you, doctor. See you tomorrow.
All right, welcome.